5, and the subject will be frame actions, subjects, and Lebesgue spaces, maybe later on. So let me start by reminding what we discussed last time, the very end of the last lecture. So the Web spaces sets with sigma algebra of sigma algebra of sets, which I will call the Borel sets in that set, and there is the Borel sigma algebra of a topological space. So somehow the term Borel is overused, but is the way it is. Various axioms one can impose on Borel sets, on Borel spaces, which we discussed last time, is countable separability. So I'm just reminding, I'm not defining again. When a Borel space is countably separated, if there is a countable collection that separates points. And of course, it will generate a sub-sigma algebra of the given structural sigma algebra. If I will forget, if I take the map from the same set to the same set, but at the first time I will endow it with the full sigma algebra, and at the second time I will endow it only in the sub-sigma algebra generated by a given countable separating set, this map will be measurable, and the image guy will be countably separated, countably generated. So again, a Borel space is countably separable if it has if the sigma algebra contains a countable collection separating points, and every such guy, by the identity map into a smaller sigma algebra, can be mapped into, injectively, into a countably generated Borel space. And this again means that the sigma algebra is generated by a countable collection, and it separates the points. And such a guy, as we've seen last time, I can always map into the counter set. Just by repeat this standard trick, if on X I'm having the collection AN, I will map little x here into the sequence which at the n index give 1 or 0 depending whether I am in AN or not. So whenever I have a countable generated guy, I can map it into a counter set, a standard, the Heisenberg counter set. So, and we said that for standard Polish space, the sigma algebra is always the same, and this is what we call standard Borel. So in this hierarchy, every countably separated space could be mapped into a countably generated space, and this one could be mapped into a standard Borel space. This is just a reminder of things we've seen yesterday, and now remind what is a Borel action. So take G G, which is a Borel group. So if you want, I can define this as a group object in that category, blah, 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 blah. Typically, what I mean by this, a topological group with its Borel structure, and observe that the structural map, which are continuous, I mean, the multiplication map, the inverse map, etc., are Borel. So this would be a Borel group, and you take such a thing.
What do you mean by Borel group? Don't you define what do you mean by Borel group? Do you mean a Borel space? Or
So a Borel group, let me explicitly define it. I mean, I will actually not use it, but just so you are satisfied, I will. G is a Borel group if G is a Borel space. And a group, there is a Borel space structure on it, a group structure on it, and the map, the obvious map, G times G to G multiplication, and G to G inversion, are Borel. Borel means measurable. When I associate this adjective to maps. So this is a group object in the category of Borel spaces, which I defined before. Well, I didn't specify what are the maps, but again, I said it. Maps are, when I consider Borel spaces, and speaking about maps of such, these are measurable maps, or Borel maps. But somehow, the groups that appears usually in our discussions are just topological groups, typically locally compact, second countable groups. But just to set this framework, when I say Borel action, I need G to be a Borel group, and I need a map from G into the Borel isomorphism of a Borel space X, such that the map G times X to X times X is Borel. And this map is Gx equals to X, Gx.
now you have a Borel space X, and now in which sense would you think about X cross X as a Borel space?
So there is a natural construction of a product sigma algebra, which I have implicitly here. I'm not explaining this. This is standard. The product, if I have X a Borel space and Y a Borel space, so X is endowed with a certain sigma algebra, Y is endowed with a certain sigma algebra, I can take the collection of sets on X times Y, which are squares or boxes. Something measurable from here times something measurable from here, and I could take the sigma algebra generated by these. And this is what we call the product sigma algebra, and I endow naturally X times Y with this sigma algebra, and actually this is a product in the category of Borel spaces. And whenever I write X times Y, I mean implicitly I'm considering this construction.
Why do you need two copies of X?
I don't need it. For in order to specify this property, I don't need it. But as a rule of thumb, when I do define a property of an action, I will use this map. Most of the time, I could have just ignored that coordinate, and it will be fine. Sometimes this is needed, as in the definition of properness that I gave, and most of the time it's the same. Here, I could have used the but I just anticipated the remark about it, sorry. Okay, thank you. G act on X, understood as above, Borel action. A Borel action G on X is called tame if the quotient, let's spell it, the quotient and sigma algebra on the space of orbit X mod G. So maybe let me stop here. I didn't finish the sentence. There is no subject yet, or object yet. But you can just stop and say that there is a natural construction of quotient structure on spaces. X mod G is just a space of orbit, and there is a natural map X to X mod G, and I can just push the collection, the sigma algebra from X to X mod G, and generate a sigma algebra on that space, and this space will have a universal property with respect to that quotient. So this
push, you mean that you change the images?
The images, yes. So this will be the strongest possible sigma algebra, or the biggest possible sigma algebra, such that the map X to X mod G is still measurable.
So you don't have to generate anything.
I don't have to. But maybe I will. Maybe one should think of the universal property of this. You endow this by the biggest sigma algebra, such that the map X to X mod G is measurable. So most of the time, for many actions that we do know, what you will get here is ugly. Okay? Sometimes a Borel is called tame, a Borel action is called tame if this one is counterdisciplinary. So this is the weakest property that I discussed. But it is strong enough. This is the definition. Maybe otherwise, the action is called bad. As we said, whenever we have a countably separated thing, I can map Borel space. I can map it into a standard Borel space. In particular, I can map it to a Cantor set, and furthermore, I can embed this Cantor set in the standard 0-1 interval. So I can do this to this guy as well. If so this is just this part of the definition. If G on X is tame, we may. This is a way to think. We may map X mod, or inject, morphically of course, X mod G into 0-1 and have a G invariant map from our space X to X mod G composed with that 2-0-1 with fibers, well, over points in the image. I mean, the fiber of a point here might be empty, but if not, fibers being G orbits in X. Okay, so this is somehow why tame actions are so important. Then you have a nice orbit space. Now let me, maybe example I will give. The actions of U on R2 that we discussed is 10. So I will give more on that in the future, but this is just to relate it to something we discussed. Here is a picture of the orbit structure on R2. And you see that, well, the orbit space is just a copy of R star. This is the orbits away from the x-axis, disjoint union of a copy of R. And if you want to think about the topology on the quotient space, it is not a Hausdorff topology, right? Because, well, these points, well, figure it out yourself. It is a T1 space, but not T2. But this point and this point could not be separated by open sets. But surely they can be separated by measurable sets, and so measurably the open space is nice. And now I want to switch to another subject, or maybe.
Could you give an example of wild action?
Yes, or maybe I'll give one more example of tame action, just to illustrate one more remark, and then I will explain wild actions. But actually, if you think of it, I'm not repeating examples that already appeared in the first hour of my talk. Then I didn't give definition. I gave this example as an illustration. So here is the A structure. A means more or less. A is the diagonal group in SS2. And now that I'm not proving it now, but this is again just an example. I leave it to you to figure out. The shift action of, say, Q on R is wild. You don't have an isometric space. So it is an exercise to prove that R mod Q is not countably separated. It will follow from things that we'll see in the future, but it is maybe one should do it himself. The SL2Z action on R2, standard action, is wild. Typically, ergodic actions, if not transitive, are wild. And I will discuss all this more formally in the near future. Again, this is just to have some pictures in mind. Questions? Okay, so now I want to hold this discussion and to pass to some discussion in general topology. Okay, because most of our examples of standard Borel spaces, etc., are coming from topology. So here is a definition, holds in for every topological space. Given a topological space, the collection, the term of constructible states is just the algebra, not the sigma algebra, but the algebra generated by the open set. So take open sets, you're allowed to take finite intersections, unions, and complements. So of course you have closed sets. You have intersection of open and closed sets. You have union of such. Here is a constructible set in the line. I mean, you can consider this as a constructible set in the plane. This is the intersection of the real line, I mean the closed x-axis in the plane, closed set, with the open 0, 1 strip. Okay, so this is a closed set. I could have taken this to be closed. I could add here a little square with part of the boundary, etc., etc., etc. These are the things that appear. Here's maybe another definition. A set is
by one set or collection?
constructible sets one set is constructible if it is an element of that collection.
So these are plural form, but it's open sets.
Thanks. Let me just say it. I'm slow with them saying hints. A set is locally closed this is a term. If it is the intersection of a closed and open set. Intersection of two sets, one closed, one open. So I have the collection of all locally closed sets. So this is the easiest description, but in a minute I will explain the term, why it's called locally closed. Exercise.
You mean just two or you mean finite?
No, just two.
Just two.
Well, if you take finitely many open and finitely many closed, then the intersection is. Yeah. But here I'm not allowing unions. When I define constructible sets, I allowed also finite unions. Exercise, easy one. Every constructible set is a finite union. So this is like a basis topology. Is a finite union of locally closed sets. This should be very easy. And now, just for a better understanding of what locally closed set is, I'll give the following easy exercise. I'll not do it myself, but I really encourage you to do it for a topological space X. Well, maybe before finishing, let me emphasize these terms and definitions are good for every topological space, need not be Hausdorff, for example. I will use next week these terms when I will consider the Zariski topology of an algebraic variety. So it makes perfect sense. And it is very useful. But also, we should use our Euclidean intuition when considering such sets as well. For a topological space X and the set A in X, the following are equivalent. I'm describing what is to be locally closed. 1, A is the intersection of an open and closed set. 2, maybe not, just 2 here. The closed set that I'm intersecting with could be taken to be the closure of A. This is very easy. A is open in its closure. So if I take the closure of A, this is a nice subspace of my space X, not just arbitrary subset X. You may think of it as a subspace. And in this subspace, A bar, A is open. So locally closed, in a sense, is not much more than just open sets. In that term, after restricting ourselves to a smaller universe. And 3, mainly I give this in order to explain the term locally closed. Locally, A is closed. Let me make it precise. For every A in A, there exists open neighborhood UA. So this is an open set in X containing A, such that, restricting to this guy, A is closed. Now here is an exercise. Make questions about it? This is all very easy. You can give it to your students in points of topology. The following exercise is not hard as well, but don't give it to your students with no hint. Although it seems harmless, if A is constructible inside some X, which I'm not writing down, then there exists U in A such that, which is U is open in A bar, in the closure field. Every constructible set contains a dense open set of its closure. Again.
No, but could you be empty?
Open and dense, you mean?
Open and dense.
Oh.
Thank you. Open and dense. So not so. These guys are not so far from being locally closed. Somehow, every constructible set can be decomposed. I mean, we know by this exercise somehow that every constructible set can be decomposed into locally closed. But there is some sort of a canonical decomposition. You can take in the constructible set the biggest locally closed piece. This will be your U. And if you remove it, you are left with something else. And you take the biggest locally closed piece in that one and remove it, etc., etc., etc. And this process must terminate after fine-tuning steps. So this is how to solve this exercise.
So sorry, what's wrong with just taking the U, the A is intersectional?
It's U in A. U is in A.
Just
So,
intersected with A bar.
so A is not assumed to be locally closed. If A was locally closed, then this exercise is stupid, yes. I'm not assuming, but actually A contains a biggest locally closed piece in it. And this will be that U. And actually, so you just, when you solve this, you just have to define what is the biggest locally closed piece in A. And this will be it, but in order to prove it, you should then discuss what happens if you remove it and continue doing this. You should see that after some time, many steps, you're done. Okay, it's a nice way to remove some time. No claim. Or maybe, I didn't mean to write this down here, but here is a remark. I will not actually use it, I think, but just for context. We may define the notion of constructible map. Between topological spaces. Continuous maps, of course, such that the image of the constructible set is constructible. We may define, you may use this sentence as a proper definition, just formulate it in this way, I don't know why. We may define the notion of a constructible action, constructible group action. A continuous group action G on X. What is a continuous group action? I didn't define this. X is assumed to be a topological space. G is assumed to be a topological group. The map G, we will have a map G to omega of X such that this map is continuous. And now you know what the definition of a constructible action. A continuous group action G on X is constructible if G times X to X times X is a constructible map. I think not. I didn't think about it enough now. Probably I knew this answer is the target standpoint, but not now. Exercise. Maybe an exercise related to this lemma. Exercise. Use the exercise upstairs to show that for constructible maps, for constructible actions, orbits are locally closed. So usually when I describe a nice topological action, I'm saying the orbits are locally closed. You may ask, why don't you demand that the orbits are constructible, which is somehow more natural? It happens naturally. If the orbits are constructible, they are actually locally closed. And the orbits are constructible if the action is constructible. Okay, I leave this as an exercise. The next claim is relating that topological discussion we had now with tameness of Borel actions. So if the action is constructible, if orbits are locally closed, in fact, acting on topological space, then the action considered in the Borel category is tame. This is the next claim. Take X, second countable topological space. When I'm taking a topological space and I want to consider it as a Borel space and I want this space to be standard, I better have X second countable. and some continuous action. When I write this, implicitly it is a topological group. Or maybe I should have, let me raise this and write to Polish. Is your permission? Just, no, sorry. Second calculus is okay. The right generality. Here. If the orbits are locally closed, for example, if the action is constructible, then G on X is tame. If I forget topology and consider it as an action as a Borel action, maybe is a tame Borel action. Explanation is very easy. The image of a countable basis of X in X mod G takes X as, by assumption, a countable basis, take its image in X mod G. These are measurable set by the definition of the sigma algebra of X mod G. Is separated points. Is point separates. Okay, and again, this is very easy, and I leave it for you to observe this, to fill in details. Okay, some more observations. The following observations in the following observation, I want to consider measures on countably separated spaces. Somehow. Many times I'm having a measure on X, maybe ergodic, and I want to push it down to X mod G. If the measure was supported in one orbit here, the measure here would be just an atom, a delta measure, a Dirac measure. If the measure was ergodic here, the measure here will be a measure that takes only values 0 and 1. Right? And actually, because this space is nice, this in any case should be just a Dirac measure. On nice spaces, 0, 1 measures must be Dirac measures. So this is the next observation. On a countably separated space,
in the claim, you assume that X is second countable. Do you assume some separation axioms yet?
Oh, yes. Yes, T0 is enough, I guess. But I will, in real life, I will assume the X will be a house of nice space. A nice house of space. Yes. It's X mod G that might be added. But for what we need the topology to separate points. T0 means topology separate points. On a countably separated space, every 0, 1 measure, 0, 1 measure is a measure that takes only values 0 and 1. Is a delta measure. delta measure is a measure which is supported on a single point. Shall I explain this, or shall I leave it as an exercise? Well, maybe I'll briefly explain this. You have a measure which is 0 and 1. You have the countable collection that separates points. Just I will assume that my countable collection is closed under completion. It's countable. And I will take all these guys in the collection which have measure 1 and intersect them and see what is left. I claim that what is left should be 1 point. If I have more than 2 points there, I can separate, one of the guys separates them, and...
So you said that there is some regularity condition. If you go to the closure, you...
No, there is no measurable structure, and no topological structure here.
So could you repeat the argument?
Yeah. Yes, I'm living here on a space, on a void space.
0-1 measures are sometimes called ultrafilters, and not all of them are principal, which you claim.
These 0-1 measures are sigma additive. Ultrafilters are finitely additive 0-1 measures. And I'm assuming here, whenever I'm using the term measure, I'm assuming sigma additivity. And so I can, in particular, I can take countable intersections of things. This is still measurable. I can still hold of things. And if you take among your generating set the intersection of all the heavy sets, those who have measure 1, you should convince yourself that you are left with, well, you can't be empty, because the measure of the intersection should be 1 as well. And it should be 1 point. Otherwise you separate, and this or that will have measure 0, and this or that will have measure 1. Maybe I should say probability measure. My measure, I mean, the measure of the full space is not 0, it's 1. And let me continue this observation. On a countably separated space, every probability measure is either a convex combination of others, of 2 others, supported on these joint sets, or a delta measure. Maybe you don't understand what I mean here, but once I explain, it will be very clear. If you have a probability measure, either it is 0-1 measure, or some set get a measure with intermediate value. You have A, which I know is 1/2, and A complement, which is 1/2, and then I can just rescale the measure on A and rescale the measure on A complement, and my measure will be the convex combination, 1/2 in this case, combination of these two. These 2 measures which are supported on these joint sets, A and A complement. And well, 1/2 had no particular importance in what I said. It was just an intermediate value between 0 and 1. So if we cannot do this, it means that my measure is 0-1 measure, hence a delta measure. Here, Now here is a fancy way of reading this last observation. Consider the trivial group action on that space. Or maybe consider the action of G on that cell, on that space, but a trivial action of a non-trivial group. When G acts on X mod G, which is what I have in mind here, on X mod G still acts, only trivially. And if you have an ergodic measure on that space, it has this property. It's not a convex combination of two things. It must be a delta measure. Okay? So this statement here, basically, and I will come back to this, but basically it means whenever X is a tame action, maybe whenever on X I'm acting with locally closed orbits, every ergodic measure is supported on one orbit. Okay? So let me end this hour with this remark. I will go back to this more formally in the next hour.